Okay, so hello everybody. Okay, so today what we're going to do is we are going to answer a question from a previous final exam for the course that I'm taking now, which is Organic Chemistry 2. If you're interested in the specific final exam for students who are taking the course that I'm taking, this is, I believe, the Winter 2016 exam, question 11, part D. So we're going to go through kind of how we're going to solve this synthetic question. So the question says, propose a synthesis for each of the following compounds, show the reagents and reaction conditions required for all steps, as well as the structure of any intermediates formed. Note, you do not need to show your retrosynthetic binding or mechanism, right? So the reason why I want to go through this question, first of all, is although for students who are in my course, you could see the answer pretty easily because they're posted on the course website, but I want to go through the thought process, how to think through these types of questions, right? Because it might frighten you initially, like sometimes the compound, your starting material and your final product are completely different. In this case, it's not that different, but we just want to figure out the thought process here, right? So first off, you could see that, okay, you have this cyclohexane and it's repeated in the product, so we don't have to deal with that, and you have this ethyl group coming out of it, and this ketone group will ultimately have to be reduced to an alcohol, right? And we have to somehow get rid of this ester group here and replace it with a what is that? An propyl group, right? So first off, the problem that we have is we have a couple of alpha hydrogens, right? So we have one alpha hydrogen here, which is, sorry, okay, that's bad. We have one alpha hydrogen here, right? And we have one alpha hydrogen here. And so we know that these alpha hydrogens are acidic, and we will have to deprotonate it somehow to get this propyl group on it. So that will be my first step, right? Um, that's how I would go about it. So we will, actually, it will not be a equilibrium. Okay, so the first step is to somehow get this propyl group on there. That's what I would do. Because the thing about this ester group here on how to remove it is, if you notice, this ester group is right beside another ketone. Now, we know that when there's an ester or a carboxylic acid beside that has a beta ketone, if you will, or a beta carbonyl, we could do a decarboxylation reaction. And that's a really easy reaction. All you require, I believe, is heat and acid, right? So that's the way we'll remove the ester. But before we remove the ester, we want to get the propyl group on it. Now, if we remove the ester before we get the propyl group on it, imagine we just remove this ester for a second, and we ended up with this compound here. Now, the problem is with this is to get the propyl group on it, right? Sorry, that's butyl group. To get the propyl group on it, right? We'll have to somehow select this specific uh, alpha carbon instead of this one. Now we can do that. It's going to be a little bit harder to do in this case here because they have really close acidity. One is a little bit more sterically hindered than the other, so you could use a large base like LDA to target this specific alpha hydrogen versus this one. But if we look at what we're starting with, if we don't remove the ester first, the thing about this alpha hydrogen here, and I'm going to actually use green to color this one here because it's a special alpha hydrogen. This alpha hydrogen is a lot more acidic than the other one because it's between two carbonyl groups, right? So the electron density between the carbon and the hydrogen is being pulled away from by this carbonyl and this carbonyl, right? So this is a lot more acidic and we can deal with it a lot more easier. So what I want to do first is I want to add some sort of base to deprotonate that alpha hydrogen specifically, and then once it's deprotonated, all I need to do is add an alkyl halide, so a propyl alkyl halide, right? It's as easy as that. Now the thing is, with the base, you want to be careful. So usually what I see students do when I'm marking exams is they use NaOH. And that's, in this case, that's fine, but sometimes you want to be careful because if you use NaOH, it's going to convert the ester into a carboxylic acid. And sometimes, in this case, it doesn't matter again, but sometimes you don't want to convert that ester to a carboxylic acid. So what you do is, here's a neat trick. Instead of using NaOH, sorry, instead of using NaOH, you use sodium methoxide, right? Now that's a base, but the thing about this is, even if the methoxide group replaces the ester group, you still end up with the same compound, right? So it doesn't really hurt at all. Sorry, that's a, why did I mess with it? Okay, right? So that's our first thing we're gonna do, step one. So what's gonna happen is this sodium hydroxide is going to deprotonate the alpha hydrogen that it's highlighted, and then the enolate is basically going to attack this alkyl halide. So what you're gonna get is something like this. And I'm going to use blue to highlight what we added, right? So that's what you're going to get after the first step. Okay. Now if you use sodium hydroxide in this case, you'll see why it's fine to use sodium hydroxide in this case, because you're just going to replace this with a carboxylic acid, and then we're still going to do a decarboxylation eventually, right? So now we have to think, okay, do I want to remove the ester first, or do I want to reduce the carbonyl? Now the thing is, when you're reducing the carbonyl, you have to, if you're going to reduce the carbonyl first, you have to be selective, right? Because you don't want to reduce this ester, because if you do, then you're not going to be able to remove it. So it's better to remove the ester first and then reduce the carbonyl, right? So to remove the ester, all we have to do is add acid, right? And just to be a little bit more scientific in this case, I'm going to add HCl and H2O. That's what you would add in a lab, right? And you're going to heat that solution up. Now I'm not going to go through the mechanism of decarboxylation in this video. If you want me to go through it, by the way, I forgot to mention we're going to have a live stream this Friday. It's going to be during the evening. I'll post the exact hours in the description in the video below and in the description of the video when I post it on Facebook, Instagram, and Twitter. So I'll get to that, the dual pole part later. So now we're doing the decarboxylation, right? We don't need a carboxylic acid because the thing is with this, once you just add the acid, it's going to convert the ester into a carboxylic acid, right? But with the heat, it's going to decarboxylate. So what you're going to get is, you are going to get this compound here plus CO2, because that is the product of decarboxylation. And you'll probably also get a little bit of methanol in there too, right? But CO2 and methanol doesn't matter. We're focusing on this guy here. Now the last step. Now you want to get to the product, right? And this is easy. All you need to do is, in the first step, you want to add NaBH4, which is our reducing agent. And then 2, you want to add some water. Or sorry, some water, or you could also add some acid because you just want to protonate the alkoxide group that's going to form, right? So you could just add some HCl and water, but you want to be careful actually, because HCl and water works, but you just want to be careful not to heat this up, because if you heat up this compound here in acid and water, what's going to happen is you're going to get a dehydration reaction, and that will actually, instead of forming that final compound, you will form this instead, right? That's what happens if you add heat. So don't add heat, just add acid. and water, or you could just add water and that should actually be enough, right? So just to be safe, actually in this case, let's just add water. And you're going to get that final compound. So that's the thought process of how I would go about answering this question. In synthesis questions, what always matters is the order in which you do your reactions, right? Because as you see here, if we remove if we have removed the ester group before we added this probyl group, then we would have had a problem of which alpha proton will be deprotonated. But because we had the ester group, this alpha proton that's highlighted in green is super acidic, and so that one will be selected, right? So I hope you guys enjoyed the video. As I said, based on the doodle poll, we are going to have a live stream Friday. I believe it's going to be around 7 or 8 p.m. But I will let you know. I just have to check the doodle poll again. The whole point of the live stream is for me to basically answer your questions, kind of like office hours, right? If nobody shows up, which is a very uh, possible outcome, I will just be answering questions on my own. But hopefully, I'm hoping to get a couple of people just so that we could have a conversation and kind of I could answer your questions and we could de-stress before the exam on Saturday for the people who are in my course. Thank you very much for watching. If you like the video, subscribe, hit the like button, and also hit the bell icon. Thanks.